Did you know that when we solve really complex, high-degree polynomial equations, well, often we're just settling for an educated guess?
Hmm.
That's right. We use numerical approximations, and inherent in that is, well, an element of error, always.
It's true.
But what if there was a way to find exact symbolic solutions, for these mathematical challenges that seem almost insurmountable?
It's a fundamental shift, really. That quest for absolute precision in these really complex scenarios. It's been a long-standing challenge in mathematics.
And that's exactly what we're diving into today. Ezouidi's theorem. This isn't just about getting a little closer to the answer.
Not at all.
It seems to completely redefine how these polynomials are solved. It moves us from, good enough approximations to perfectly exact solutions.
That's the claim.
So our mission in this deep dive is to understand how this theorem gets those precise, exact symbolic solutions, even for something as intimidating as the 16th degree polynomial.
Yes, that's the example we'll look at.
And we're going to compare it to those classical numerical approaches, just to really highlight its power and precision.
Sounds good.
So, okay, let's unpack this. Why have high-degree polynomials been such a headache for mathematicians for so long? What makes them so, well, notoriously difficult to solve with traditional methods?
Well, what's fascinating here is how traditional methods really hit a wall when you're dealing with these higher degree polynomials.
Right.
Techniques like, say, Newton's method, which are incredibly useful for many things.
Sure, yeah.
They only give you numerical approximations of the roots, and that comes with inherent risks.
Like rounding errors.
Exactly, rounding errors, and crucially, they just can't guarantee exact value. They can get you incredibly close, remarkably close sometimes, but never perfectly definitively there.
So it's like trying to hit a bullseye with a dart, but you're only guaranteed to land somewhere on the board, maybe close, but never truly dead center. It's always the best guess, pretty much.
That's a perfect analogy, yeah. And this pursuit of the bullseye, it isn't new. For centuries, mathematicians wrestled with this exact problem.
Okay.
In fact, a huge moment came with Abel's theorem. This actually established why some of these higher degree equations seemed, well, impossible to solve exactly using certain methods.
Ah, right. Abel's theorem.
Yes. It states that certain polynomials, specifically degree 5 or higher, generally cannot be solved using radicals.
Radicals meaning?
Meaning you can't find their roots just by using combinations of addition, subtraction, multiplication, division, and taking nth roots, like square roots, cube roots, etc.
Okay.
So this really set the historical context. For a long time, it was kind of accepted that exact solutions for these higher degrees were, in a classical sense, often impossible.
So for a long time, the mathematical world essentially said, look, beyond a certain point, degree 4 maybe, don't even bother looking for an exact formulaic answer. That's a pretty strong statement.
It was, based on the tools available.
How then does Ezouidi's theorem manage to cut through these limitations? How does it offer something fundamentally different?
Well, this raises an important question about what we've historically considered solvable,
Yeah.
Ezouidi's theorem presents, a groundbreaking approach because it seems to completely bypass the limitations of both classical algebra in the sense of radicals and numerical methods.
Okay, how? What's the core idea?
Its core principle is the derivation of exact symbolic solutions, not just approximations.
Symbolic meaning, like not decimals.
Exactly. Think of it like this. Instead of getting a decimal approximation like, say, 3.141599, you get the precise mathematical expression itself, like writing pi or the square root of 2.
Okay. The actual mathematical entity.
Precisely. It's about finding the perfect formula for the answer, not just a number that's close. And this is really significant because, contrary to, or maybe alongside Abel's theorem, Ezouidi's method demonstrates that even polynomials that seem to defy those radical solutions can apparently be solved exactly. It just uses a different kind of precise, systematic process. It really redefines the notion of what might be possible.
That is a truly revolutionary claim, especially when you think about Ayle's historical impact. It almost sounds, well, a little too good to be true. I'm definitely keen to see this in action. Do you have a specific example? Maybe that 16th degree one?
Absolutely. Let's tackle that. We are going to look at a truly formidable equation today, a 16th degree polynomial.
Right.
Imagine an equation so long and intricate it would fill, half a page on paper, dozens of terms, big coefficients.
Right.
Traditionally, just looking at something like this would send most mathematicians straight to their numerical approximation software.
I can practically feel the headache just thinking about it. The sheer length and complexity.
It's daunting. It is indeed a beast. For this polynomial, the highest power of x is 16, so we say n16.
Yeah.
And it has a specific set of coefficients, these numbers multiplying the powers of x. We call them its L values.
Oh, yes.
Like L sub 0, L sub 1, L sub 2, and so on, all the way up to L sub 15 for a degree 16. Each of these numbers holds a specific place and value.
Right.
And that brings in those unavoidable errors.
But Ezouidi's theorem sidesteps that.
Completely sidesteps it, yes.
So, okay, if it's not about approximations, how does Ezouidi's theorem systematically break down this massive polynomial? How does it reveal its exact roots? What's the actual process like?
This is where the ingenuity of the theorem really unfolds. The method involves a brilliant recursive process.
But recursive, meaning it kind of loops back on itself.
Yeah, in a way, yes. It systematically finds what we call S terms. These S terms are exact symbolic values that are calculated based on the original polynomial's L values.
Okay. S terms derive from L values.
Right. And this process effectively transforms the original super complex polynomial into a much, much simpler form expressed using these S terms.
Can you give us a sense of what that recursive process looks like without, needing a PhD to follow along?
Let's try. Think of it like a sophisticated step-by-step algorithm or recipe. At its heart, the theorem uses a powerful general formula to calculate each S term.
Okay.
We don't need to recite the whole formula. It's quite complex looking. But the crucial point is how this calculation engine meticulously processes each term of the original polynomial.
Right.
For instance, it uses things called binomial coefficients. You might remember them from algebra, like in Pascal's triangle.
Vaguely. They pop up in combinations.
Exactly. They're just specific numerical factors that adjust the terms correctly in the calculation. The formula also involves the degree of the polynomial, n, and importantly, it references the earlier L values and previously calculated S terms.
So each step depends on the ones before it.
Precisely. Each step in the recursion builds exactly on the previous ones. It creates this chain of purely symbolic calculations. No approximations are introduced at any stage.
And if I'm understanding this correctly, the real breakthrough, the aha moment, is that each of these S terms is determined symbolically. There are no decimal places anywhere, no rounding, just pure exact mathematical expressions.
That's it. You got it.
Which completely eliminates any possibility of numerical approximation errors.
Exactly right. That's the core strength. And for our specific 16th degree polynomial example, well, the results of calculating these S terms are quite fascinating, maybe even surprising.
Oh, how so? What happens?
When Ezouidi's theorem processes this particular polynomial, a really remarkable simplification occurs. Out of all these potentially complex S terms it calculates, almost all of them, surprisingly, resolve to zero.
Wait, zero. So nearly all those terms that contribute to the original polynomial's monstrosity, they just vanish when you convert to S terms.
They do for this specific polynomial structure. It chromatically simplifies the equation.
Wow.
We're left with only two crucial non-zero S terms out of, 16 potential terms. One associated with the by 8 term and one constant term.
So that massive page-filling polynomial collapses.
It collapses down to a much, much simpler form. Essentially, it becomes by 16 plus one of our non-zero S terms times by 8 plus the other non-zero S term, all equaling 0. It's a transformation.
Incredible. That's like finding a hidden, super efficient shortcut through a dense mathematical forest.
Okay, so you have this wonderfully simplified form. How do we get the final roots from that? Yeah, once you have that drastically simplified equation, Getting the exact symbolic roots is actually quite direct. It's basically like solving a quadratic equation, but 4 by 8.
Ah, okay, I see.
You can use a formula very similar to the quadratic formula to solve for by 8 first, and then to get x itself, you take the 8th root.
Right.
And the final roots, the actual solutions for x, are expressed very elegantly using something called complex exponentials.
Complex exponential.
Oh, okay.
Sounds fancy.
Don't let the term intimidate you. They're just a really powerful and precise way to represent numbers that involve both magnitude and direction. Think of points on a circle in the complex plane.
Okay.
In this context, they provide the absolutely precise, exact form of our 16 roots. It's a direct and frankly quite elegant outcome of these meticulous recursive steps we followed. No approximation needed.
What's truly fascinating here, I think, is that we're looking at something profoundly different from what most people, even those with some math background, understand about solving complex equations. This isn't just a clever mathematical trick for one specific case, is it? It feels bigger than that.
I believe so. No, not at all. This example really highlights the crucial difference between precision and approximation, and it has potentially profound implications.
Like what?
Well, first, the roots obtained are exact. They are not subject to the compounding errors or the inherent limitations of numerical methods.
Okay, absolute precision.
Second, it means Ezouidi's theorem seems to provide precise, solvable roots for types of polynomials that were previously deemed unsolvable by classical means, or at least only approximable.
Right. It overcomes that historical barrier we talked about.
Exactly. Imagine the implications for fields like, say, quantum physics, where tiny errors in calculation can cascade into massive discrepancies in predictions.
Or maybe complex engineering problems.
Or engineering, yes. Where exact calculations for stability or resonance could mean the difference between a structure standing firm for centuries or, well, failing unexpectedly. It's really a testament to the power of finding the right systematic, precise, recursive derivation process. And it fundamentally reshapes our understanding of what constitutes a solvable problem in mathematics. It suggests the category is perhaps broader than we thought.
It truly does. This whole deep dive into Ezouidi's theorem, it leaves us with a pretty provocative thought, doesn't it? What other mathematical boundaries, what other problems that we currently label as unsolvable or only approximable, might actually yield to similar innovative theoretical frameworks?
It's a great question.
How many other exact solutions might be out there just waiting to be uncovered, where we've maybe prematurely accepted that only approximations are possible?
Yeah.
It really makes you wonder how much more there is to discover and how fundamentally our understanding can shift, sometimes dramatically, just with new approaches, new ways of thinking.